cool. It's like the original, like from '97.
There's some old ones, yeah. Good morning, everybody online. Does anybody need me to do their attendance? Okay.
Yes, please.
Okay, so that was Caden who said yes, Jack, Kyle, Cattell, Lynette, did you say yes? Okay, you are welcome. Everybody online, don't forget to do your attendance. Okay. So just two quick announcements as screen is warming up and turning on. I have gotten a fair number of emails from everybody across a lot of the classes about some errors in the quizzes. I'm not sure what happened because both Christy and I reviewed them. We really missed some confusing worded questions, some errors in questions. So I apologize.
Like from last week, like we should have taken, or we should have done some of the answers last week, and then from last week we should have done them this week.
Okay, yeah, I'm not sure what happened because we both looked at them, we both reviewed them, we thought we were set. So I apologize. If you find those, please do keep emailing me. I'm correcting them. I'm going to try and go through the question bank for the next set of quizzes before they open and try and make sure we don't have that problem. I know that one of the things we did do is we tried some different styles of questions. So not just, select one answer, but select multiple. Noodle got very upset with me when I first tried that. So there was a select multiple question that I had just multiple problems with. So I apologize. If you see errors or you think something's wrong, save your quiz and send me an email. So that way you don't waste time and get a bad grade because of my mistake. So you can save your attempt and we can ask, we can figure out if there's something wrong with the question, and then you can go back. And so maybe you don't have to take it multiple times due to errors, which I know wastes your guys' time. So I apologize. You can try to catch them going forward, but.
Also, there was a question that was when we were supposed to read both chapter 3 out of the one in the online and the one in the book, cover book. And I ended up finding the question or the answer in chapter 4.
Okay. In the Reactor Theory class?
Yeah.
Okay. Okay. The most recent quiz? Okay. Okay, I'll take a look at that. Did you have a question, Joe?
There will be a capstone quiz this week?
I thought it opened yesterday. Did it not?
I don't think so.
Okay.
And the same with radiation protection, but I know that's not your class.
No, that is not.
I think Christy said she's going to make one for that one, but she's going to have help with it.
You're under pressure?
So if I put a capstone quiz in, I'll do one that's like 4 questions. So it's something you guys can handle fairly easily with the shorter amount of time rather than a 10 or so question quiz. But I'll see what happened on that. Morning, Sam. You what? So the class I'm taking, the teacher has her Moodle set up to do this one really cool thing where when you're done with the week that's at the top, it moves to the bottom.
I like that idea.
So yeah, whenever you open Moodle, like what you're doing that week is right at the top. So
Then you don't have to
scroll forever. Yeah. So I asked her how she did that, and I'm gonna try and do that when she tells me, because I thought it was great and easier to use.
The end of the semester, I'm like going to the bar.
Well, especially when you put those pictures like in the boiler and turbine class, I'm like, oh my god.
Yeah, and unless I have a link, they won't link them. Like if I try and upload it, so like you can download the picture as a link, it has to be linked from somewhere. Because I don't necessarily want like just random weeks to have a big old picture, but it won't display. It doesn't give me options to display it a different way. Yeah. There's a few things I really hate about Moodle. There's a few things I really like. Okay.
It'd be nice if like every instructor was all on the same page with Moodle, because it's kind of frustrating going into a class when you have some who really excel at it and use it, and then others who have like never seen it before. Yeah, university didn't make them learn it. They don't care to learn it.
Well, and so like just coming in where, you know, Mike had not left syllabi, course content, textbooks, course structure, anything in Moodle to like give me an idea of where to pick up and start teaching. I really like that Moodle creates a record of what the class has done. I like that I can show the ABET accreditor who's coming in a couple years, like, this is what we've done. Here's how we're consistently getting those objectives, you know, that we're required to keep the accreditation. There's a lot of utility in it, but I think that it was created by people who are not instructors. So it's like, oh, this would be a good idea, but it's not quite functional in some ways.
I know this, but I can't remember what property it was.
Yeah.
Are you guys enjoying that class?
Yes.
You bring down some pretty cool sources last week. Get to look at.
Wow.
You what?
I heard he did.
Okay, let's jump into talking a little bit about the problem we were working and reactivity.
Is this still the neutron life cycle PowerPoint?
Yes, there's going to be less from the PowerPoints this morning, but that is still the topic. Okay, does anybody think they can draw from memory our life cycle?
Not from memory.
Not from memory. Anybody online, you think you can walk me through drawing it?
I'll give you most of it.
Most of it?
I could look at my notes once. I could do it. Yeah, you can draw the life cycle. All from that.
Not from memory? Okay, all right. Does somebody want to volunteer to do it from their notes?
I'll do it for my notes.
Okay, all right, go for it.
Whoops.
Did you say we were gonna do this question? I thought we were gonna go at all.
No, I think we have to do Thursday.
So once they get to write down, like if you needed upvoted.
I'm gonna, well, I'm gonna upload it, but I don't know who it's from.
Dude, you look tired.
I'm tired.
I think it was great.
I woke up this morning, my eyes weren't opening. Pretty good. My kid put chips in my pocket. Found out.
Pretty nice, actually.
Yeah, yeah.
Breakfast.
Except he's never nice about anything, so he's smashed.
Your clothes.
He's the Sour Patch Kid. He'll do it with like a smile as he's like burning your world down.
Sounds good.
My wife made 2 sandwiches today. Man, she gets it, takes it inside her, feeds it to the dog.
Oh.
And he knows better.
Kenzie, for the IML Teams meeting today, is that something you can have up in here too, or should we just talk on our own?
You can do either. Christy is gonna have it up in here. I actually am gonna have to cancel my office hours this afternoon.
Yeah.
Thank you. I have to go put my dog down.
Oh,
Yeah.
sorry.
But Christy will have it playing here.
Both of them, you said?
Just one. Just one.
What about the ANS?
Oh, yes. She'll also be playing that in here.
There's an ANS one at 10.
Yep, ANS extra credit at 10 on low dose radiation. And the INL internship information session
And
at
then
11.
Another one at noon, correct, for each student.
No, you read that wrong.
I thought there was one at 10 as well.
It was 11 Central Time, so if you can,
Okay. So, where does our first generation of neutrons go into the cycle?
Top level one.
In one. And after we have our fission, we have N2. N2. Comes out. Okay. So if I were to ask you, say N1 equals 40,000 neutrons. How many neutrons are going to be absorbed in the fuel? For those of you online, if I have, and let's say that epsilon is let's use the same numbers from yesterday. Epsilon is 1.031, and I'll write these up here. Let me just write them for those online. Let's say that our fast non-leakage factor is 0.89. Resonance escape probability is 0.73. Our thermal non-leakage is 0.96. Our thermal utilization is 0.82. And our reproduction is 2.102.
20,893. What's the number of thermal neutrons absorbed by the fuel?
What answer did you get?
28,893.
Got a slightly different answer.
26,794.
Still got a different answer.
2191.
That's what I got, 2192, 21,092.
That's what I got. Okay, so online, what'd you guys get? Yes, Sam, you would. Right, so if I'm asking you how many neutrons are absorbed in the fuel, which step are we at?
P.
Okay, why P?
21,091.
That's what I got.
Because that's the absorption without slowing down. I mean, I don't know.
Okay, someone said F, why F?
Absorbed in the fluid that has.
Okay, so from F, we have everything that gets absorbed, right? Here, out of here, there's some that are just absorbed in the reactor structure, right? And then the ones that are absorbed in the fuel go on to create fission right here, right? So we are at F. Right here, this number coming past our thermal utilization factor are going to be the number that were actually absorbed in the fuel. So right here, these are the fast neutrons that are absorbed into our resonance peaks before they slow down. So the technical name for this is resonance escape probability. And so while they are absorbed into our resonance peaks as fast neutrons, and only those that escape continue as thermal. So this would be the number of neutrons that slow down to thermal energies. We then have some leak, and then we start getting absorbed as thermal neutrons. So to get the number of neutrons absorbed in the fuel, I got the same number as Amber. You would multiply your 40,000 times 1.03 times 0.89 times 0.73 times 0.96 times 0.82. And that's going to give us the number absorbed in the fuel, which was what, 20,000? 91,092. Everybody see that? Everybody end up with that number now? Okay. Okay. All right, Sam. Sounds good. So let's again assume that we have 40,000 neutrons in N1. How many neutrons would be in N2 if this was an infinite reactor?
44,335.
And how did you get that?
Just times all of them together. Like 40,000.
All 6 of them?
Yeah.
No.
What?
An infinite reactor. What do we not have in an infinite reactor?
Leakage.
Leakage. So what's K infinity?
Infinity, you said yesterday would equal the epsilon times F times the eta times P or rho.
This one is P.
Okay, P.
Rho is when we talk about reactivity. Exactly. So if we have an infinite core and we can't leak, we don't include leakage. We use the 4-factor formula. So for those of you who are online,
You said that's not P or is P?
that's a P. Right now we've got a P. In just a moment, we'll have a row. Yes, 51,891, that's what I got. So that will be our second generation of neutrons. What is K infinity? Just our K. Just our infinite multiplication factor, right? So if I ask you how many generations are in N2 in an infinite reactor, I'm asking you to multiply this times this. Now, if I'm just asking for the infinite multiplication factor, I'm just asking for these four. 1 point, what?
2973.
Okay, yes, that's what I got.
Can you say that again about
Yes.
the infinite one?
Online, you guys calculating K infinity? So I'll make sure they're following. Okay. All right, as long as you guys are following along, I'm not leaving you behind. So, because, as we said, this is both a mathematical representation, right, an equation, and a physical representation, what's happening at each step. I can ask many different ways to get information from this, right? So the first thing I asked was, if your N1 has 40,000 neutrons, and you have an infinite reactor, what is N2? And how did we calculate this?
40,000 times B times N times N times 2.
Exactly. Now I'm just asking for our infinite multiplication factor. So you could find that by multiplying these four. You could find that by putting those over each other, right? Does that give you the same answer? Here, I can make that a little cleaner for you.
Okay, I thought it was RV.
I thought it was a P.
I'm like, I don't know what that is.
Like, where did the B come
Okay,
from?
that makes more sense.
So those are the ones that leak. And then there's a little P here. Does that make it a little better for you?
Okay, so if I use just the equation, that would be for a wording like what?
So if we did this, I'm asking for what's our infinite multiplication factor. You could also get that same answer doing this, right? If you know your initial neutron generation, and you know N2, because that's what I asked you first, right? This should give you the same answer.
Okay, but if I have 40,000 in a infinite reactor, what is it? And then, so that was the other question, is what did you do with the 40,000? I guess I didn't see that part.
$40,000 times right?
Okay.
Because we're talking about infinite right now.
That's what I thought. I should- just talking about the-
So all of this information, yes, Sam, that is the number I got. All of this information is related because the critical status of a reactor is telling us about the neutron population. The neutron population is continuously doing this cycle, and it's going to be going up or down, really honestly, based on whether or not we put control rods in or out. A few other factors happen, like temperature, fuel burnup, but our biggest piece we influence is moving those control rods. So I can ask you from the information on this little diagram about K infinite, K effective, neutron population, number of neutrons that leak, number of neutrons that slow down, number of neutrons that are born fast, right? And all of that information is in some piece of this puzzle and related by one of these equations or more. Is that making sense to you guys? I know it's a lot that is the same in a lot of ways. Yeah, Katie.
So after the fuel fission, all neutrons are born fast. So what is the 1.0314? If it's already coming out with what, I don't know, it was like 57,000.
So this is how many of our fast neutrons immediately create a fast fission.
Oh.
Right? Because there's some amount of U-238, U-236 that's in our fuel, right? Because we only enrich to 3 to 5% U-235. So that means there's 97 to 95% the other isotopes of uranium. And so we absolutely get some fast fission. We want to operate our reactors to drive this number low, right? As close to 1 as possible is a good thermal reactor design. So you'll always see in a thermal reactor your epsilon value be very close to 1. And that's what we want. But there's always going to be some, 0.03 that does create fast fission. And so those neutrons can't slow down because they've gone and created a fission.
And they just don't get accounted for when they continue to go through this.
Yeah, so that's an interesting point, right? Because when we create fission, we make more fast neutrons, right? Which means that right here, we could have a little mini loop where those fast neutrons are born and they could potentially slow down themselves, right? So what we're essentially saying is that we control our reactors so few of these neutrons create fast fission, and we don't drive our reactor on this, right? We drive our reactor here after they slow down on our thermal neutrons, but these are not going to affect the multiplication factor. However, that is why if you start to see an increase in fast fissions, you can lose control of your reactor, because all of a sudden, this little loop that might occur right here can start driving your reaction rate, and things don't get over here to slow down like they should. So that's an excellent point that we weren't going to talk about until later. Right here, there's a little loop of fast neutrons born from fast fission. When we have that so close to 1, it's so few neutrons, essentially we ignore its contribution to our multiplication. But it is there. Everybody following? Everyone feel comfortable with this? Okay.
Until you put it on insurance.
Actually, I have a quick question.
Yeah.
So after you have the thermal neutron absorption, and in this instance, you multiply it by, so 82%, right? 0.82.
Yes.
So then after that step is thermal neutron absorbed by fuel, and then past that is fuel fission.
Yes, so this factor really more goes with this statement, right?
Because you get the 2.102 is the number you have after the fuel fissions.
Right. But once they're absorbed, you multiply it by this, and that's what we get from fission, right?
Okay.
So it's still in the right order.
Yeah.
But after they slow down, we're going to absorb them. We're not going to count the ones that get absorbed in the structure, the moderator, the poisons. We're only going to count the ones that get absorbed in the fuel. So this number is telling us of all the thermal neutrons that get absorbed, how many are absorbed in the fuel. So roughly 80% go to fuel and 20% are wasted in this case, right? And then they fission, and for every fission, we're getting about 2.1 neutrons. Okay, let's see. Okay, let's talk about reactivity. Let's say that we had 30,000 neutrons in the first generation. And we had 35,000 in the second generation. And then we make an adjustment. And in the third generation, we have 32,000. Oops, I don't know how I did that. What is our K from N1 to N2? Let me put this on this board for these guys. No, we're going to use the same reactor with the same factors we used in the last problem, but this is not an infinite reactor.
Would you even need those numbers, or would you just divide them?
It's 1.17.
You can just divide. If you want to check your division and make sure you put the right thing in the right place, you can also then multiply. But you're completely right, Haley. You don't even need the other factors. Let me write this down for them online. Give me 1 second to catch them up. And that looks like 32.5, doesn't it? Not a zero. We're looking for our multiplication factor, Sam. Okay. And I'm sorry, what did you say you got?
1.17.
That is what I get. And from the second generation to the third, yes, that's what I get as well. I get a slightly different K for N2 to N3, Sam. I got exactly what you got for the first one. So we now have, oops, wrong. Okay, 1 and K2. We're going to make this K1 and this K2. This tells us whether or not our power and neutron number is increasing or decreasing, right? What's happening to power here? Going up. What's happening to our neutron population? Which also means our heat's going up and our reactivity is going up. Opposite is true here. It's less than 1, right? Have you guys all seen either in the reading or other classes and the subcritical, critical, supercritical?
Yeah, you told us the other day.
Okay. For those of you who are online, it was so, sorry, it's hard to put this online for everybody too. Okay, sorry about that, Sam. Okay, this corresponds to a reactivity as well. So now I'm going to draw our rho, right?
And rho would be the reactivity.
Yes. But now instead of comparing it to 1, right, because K is this. So what does this equal when we have no change happening in this mathematical formula? 1, right? So if N2 equals N1, there's no change, no power's going up, no neutrons are multiplying, then K equals 1. The formula for reactivity is K minus 1 over K. So if there's no change and K equals 1, what does rho equal?
0.
0. So now we're going to compare reactivity to 0, but we have the same chain. This is reactivity increasing. This is steady state. This is reactivity decreasing. This is supercritical. This is critical. This is subcritical. For those of you online, I know you can't see the board. K is N2 over N1. So when N2 equals N1 and there's no change, what does K equal? Yes. Reactivity with this rho is K minus 1 over K. So when K equals 1, what does reactivity equal? Exactly. So we can make the exact same chart for reactivity. Yeah, Katie.
What did you say those were again? It was increasing, steady state, and then decreasing?
Yes. Same thing here. Increasing power, steady state power, decreasing power. Increasing neutron generation, steady state neutron generation, decreasing neutron generation. Same things here. reactivity is a unit of multiplication. It tells us how much we're increasing, right? Because we can be above 1 and we know we're going up, but that doesn't tell us with a unit how much we are. When we write reactivity, the unit is literally delta K over K. That's the easiest one, the first one we're going to start with. There's several. So for this K1, this N1 to N2 generation in the reactor, what is reactivity? So for those of you above, for this K1 right here, what does reactivity equal? What'd you guys get? I'm going to carry it out a little further, but yes.
So if the unit is delta K over K, then that's basically not even a unit that would ever be like spoken, right? It's just reactivity would be 0.1429.
We do say it. We treat it just like seconds or minutes or feet or inches. Delta K over K.
Okay.
Our reactivity is 0.14 delta K over K. Yeah.
I got a different answer than you. Did it wrong?
You just rounded sooner. Right? Because it was 1.6 repeating.
Oh, yeah.
So remember, we're talking about small numbers and decimal points. So the more you round, the more different your answer is going to be. Yeah. We did. Right? It was 1.6 repeating.
Oh, I don't know why this gave me some.
That is correct, Amber. But what value did you get for rho? Okay, and if you guys want to go ahead, tell me what reactivity is for the second generation.
Negative 0.09.
It's what?
Negative 0.09.
Anyone else get the same answer? I didn't calculate it yet. You got a different answer?
I'm still not getting the 1
We don't need to answer that.
like I get what your equation is, but my calculator's not good.
Let me come see what your calculator's doing it. Yes, Sam, you got that right. That's going to be 0.14. If you rounded, it'll be that. Okay. Let me see what you have. Because my guess is going to be if we're about Okay, so when you're doing this in your calculator, depending on your calculator, be aware that if you write this, and I'll just go ahead and round, 1.7 minus 1 divided by 1.17, Your calculator is going to do the division first. You guys remember from math, order of operations? Division is done first. So you have to subtract first. So depending on your calculator, you might have to put in parentheses before the division, or that is going to be the error you're getting. So be aware, we subtract first, then we divide that whole answer by k. Your calculator will divide 1 by k and then subtract that from k, and that is a different answer.
So I kind of get time.
So we're just better off not even, like, if we're doing the reactivity part of the equation, just using that, like, taking the 35,000 divided by 30,000, you're gonna get the 1.1666 instead of using the 1.17 number.
I would.
Yeah.
I would not round to the end. Even then, if I realize you made a rounding error, I'm going to take less points off. If you guys make this mistake, I'm going to take more points off because this is not the equation. Right? So break it up into 2 steps, use parentheses, figure out how to tell your calculator to do this equation, whatever you need to do. Don't make this mistake.
So
Use
number
the answer
4,
key.
it's asking you to find the neutrons or that was the,
Number 4,
find the reactivity. but
what is the
it-
reactivity?
But it doesn't give you the neutron generation.
Well, it says from the reactor in problem 1, right?
Oh, okay.
What was your question, Jack?
Well, I was just saying that I just use the answer key on the calculator, so you don't have to punch it all out at 1.16667 or whatever.
Yes, that is a great shortcut. That's what I do in mine. I take the previous answer and I multiply it, and then I don't lose
That's
anything.
when mine messed up, that's what I did.
Yes,
Which mistake are you talking about at the bottom there? Isn't that how it's supposed to be inputted?
no. This is now.
Yeah. Yeah,
Yeah,
okay, yeah, okay.
This is wrong.
I tried the way you had it, I was calculating, and it didn't work. This is correct. It was like, I got like,
Okay,
maybe
so,
you just have to do the 1.17 minus 1 first, and then do like you said, the answer key.
so 1.16 minus 1, enter. Then divide that answer by 1.16. And yours is also not going out to very many digits, right? It is 0.1, it's 0.1429. I don't know how to change that in your calculator, but you probably want to see at least 4 in your answer.
That if I could get it to work.
Oh,
It gave 0.1, which is which is correct, but it didn't cut that off at just 1 decimal, right? So you're always going to be struggling. Yeah. Okay.
And the units is delta K over K.
Delta K over K.
Or decimal something.
Okay. Amber got the same number here for reactivity. Let me see what I get. Yep. So 0.0937 is what I get for this
so
one.
that would be subcritical,
Yes.
negative.
And we know that because this, right? This is essentially telling us how much super or subcritical we are, right? Reactivity limits in your reactor are going to be in delta K over K. And so when it tells you, you can put in an experiment that adds less than 0.002 delta K over K, or we also talk about percent delta K over K. We're going to talk about percent milli, another unit of reactivity, and we're going to get into reactivity a little bit later in the semester in more detail. This is just our first blush with it. So for right now, we're just going to use delta K over K as our unit. Just be aware there's more. Okay, did everyone follow what we did there? Anyone have any questions? Online? Oh, sorry. Did you have yeah.
These generations are like happening so fast, though, you would never actually be calculating between like one and the next generation. Wouldn't it be kind of an average?
So you are going to have neutron detection equipment that is going to be able to count this flux that's happening. And so you're going to get a K or a reactivity, just depending on your instrumentation. And it's going to be displayed right next to something we're going to learn about next, which is our reactor period. Because you're controlling power, right? Here at the AGN reactor, we might control reactivity because it's so tiny. Most of the time, you're controlling power. And so reactor period takes us from neutrons to power. And there's tons of great reactor jokes about the reactor period. But it is how we go from reactivity and neutrons to power. So that's what you're going to see on your console. I'm at this power now because my neutron flux is being detected at this reactivity and this multiplication. Your instrument is going to say you're on this reactor period. And at this power and this period, you know how fast you're increasing or decreasing in power. And that's what you're going to be looking at in the moment by moment, which we'll do some rounding, right? You're not going to control out to 0.00001 megawatts, right? When you're shutting down and starting up, you'll be interested down in kilowatts and watts, but you're mostly going to be looking at your megawatts and percent full power. Does that answer your question? Yeah. Okay. Any questions online? Okay. Amber, Marcus, Jennifer, Porter, you guys have any questions?
Nope, I'm good.
Okay. All right. That's it for this morning. I don't know. I have the first years down in the reactor lab. I don't know if someone else uses this one. You guys should now have everything to do that worksheet. So take a crack at that. Do it on your own.